This lecture, we look at complex numbers and quadratic equations. Complex numbers appear naturally in quadratic equations. Suppose we want to solve the quadratic equation ax squared plus bx plus c is equal to 0. By completing the square, we can solve for x and find that x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. This is the quadratic equation. The expression b squared minus 4ac under the radical sign is called the discriminant of the quadratic equation and is often abbreviated by delta, capital delta. If delta is b squared minus 4ac is positive, then the square root of delta is a real number, and so the quadratic equation has two real solutions, minus b plus the square root of delta over 2a and minus b minus the square root of delta over 2a. The quadratic equation ax squared plus bx plus c equals 0 again has this solution by the quadratic formula, and if the discriminant is 0, then it turns out that these two solutions are really only one, because we have plus or minus the square root of 0. So we end up having minus b over 2a showing up as a root twice. This single solution occurs with multiplicity 2. Again, a third possibility is that our quadratic equation, when we find this solution, that the discriminant delta is negative. If that's true, then the square root of delta is purely imaginary, and so our solutions are going to be complex numbers which are not real numbers. To be explicit, if delta is negative, then minus delta is positive, and so the square root of delta is the same as the square root of minus delta, that real number, times I. The solution to the quadratic formula are then x is equal to minus b plus the square root of minus delta times I over 2a, and the conjugate minus b minus the square root of minus delta times I over 2a. In this case, the plus or minus sign in front of the square root of delta assures us that we will get two complex numbers as solutions, and they will be complex conjugates, coming in conjugate pairs. For example, the solution to this quadratic equation, after we apply the quadratic formula, will give me minus 1 plus or minus the square root of 1 squared minus 4 all over 3. That discriminant inside the square root is minus 3, so we could think of the square root of minus 3 as the square root of 3 times I. And so there are my two solutions. Thus the two solutions are the complex conjugate pairs minus a half plus the square root of 3 over 2i, and minus a half minus the square root of 3 over 2i. Since these are the two zeros of the polynomial x squared plus x plus 1, then we can in fact factor this polynomial. Recall that if c is a 0, then x minus c will be a factor, so my factors are x minus this first complex number times x minus the other. If I distribute the minus signs, I get this. So I've factored x squared plus x plus 1 into two linear terms. A few more worked examples. Let's instead look at the equation x squared minus x plus 1. I've changed the sign on x from the last problem. And let's factor this when we're done. By the quadratic formula, with a equal to 1, b equal to minus 1, and c equal to 1, we get that our solutions are 1/2 plus or minus root 3 over 2i. So I get these two complex numbers, and therefore if c is a 0, then x minus c will be a factor, so my factors are x minus the first complex number times x minus the second. Distribute the minus signs and simplify. And here's the factoring of x squared minus x plus 1. Let's solve the quadratic equation 2x squared plus 5x plus 7 equal to 0. Using the quadratic formula, my solutions look like this. A was 2, B was 5, and C was 7 in the quadratic formula. Let's simplify the discriminant. 5 squared minus 4 times 2 times 7 is minus 31. So inside the radical we have a minus 31. Think of minus 31 as 31 times minus 1, so that radical becomes square root of 31 times I. And so there are my two solutions. They're both complex conjugate pairs. There's one solution, there's the other. If I want to factor this polynomial using these solutions, then I notice that since I have these two zeros, whenever c is a 0, then x minus c is a factor. So I can rewrite the expression as x minus this first complex number times x minus the second complex number. And these must be factors of 2x squared plus 5x plus 7. Now, 2x squared plus 5x plus 7 does not quite factor in just those two. If we look at the leading coefficient of the polynomial, the leading coefficient of our quadratic is 2, but the leading coefficient of x minus that complex number times x minus the other one is just 1. We see that we need to take that factoring we just got and multiply by 2 to complete the factorization. 2x squared plus 5x plus 7 really factors like that. We've multiplied by 2 to fix the leading term and make sure we really get a full factoring. So there's the factoring of 2x squared plus 5x plus 7. In the next presentation, we explore the algebra and geometry of complex numbers.